Okay, welcome to the lecture 17, and in this this is considered as a tutorial class. And we'll solve few problems related to the Lagrangian, constructing Lagrangian and finding equation of motion. So just remind you the recap, remind you that in last class, so last few classes, so last few classes we are constructing the Lagrangian for various simple system. So we are constructing Lagrangian system in a constructive manner. So we have constructed Lagrangian for simple pendulum. Let me list down. Secondly, we have double pendulum. Third, we have constructed pendulum with moving support. Here we consider various type of moving support. When the support is moving along x direction, support is moving y direction, support is oscillating along y direction, support is moving in a vertical circle. So all possibility I mentioned how to calculate Lagrangian. Fourth, we consider the spherical pendulum. This was nice example to emphasize 2 points. One is a cyclic coordinate, and second thing is that use of spherical coordinate system. So these problems we discuss, and now we will consider few more problems to illustrate. For example, as I was mentioning towards the end of last lecture, that I will consider some problem where the use of cylindrical coordinate is involved. So let us write down this problem and try to solve. So problem 1 of this today's lecture, So a particle, this is a very well known problem, you can find in many textbooks also. A particle of mass m is free to slide on a smooth wire whose equation of motion in cylindrical coordinates is given by rho equal to a, phi equal to 0, not phi equal to 0, z equal to b phi. Okay. And also some initial condition is given, particle is released from rest at rho equal to a, where phi equal to 0 and z equal to 0. So question is discussed its motion. So, this is the problem. We will solve this problem. By solving this problem, it will give you certain idea, particularly how to use cylindrical coordinates, how to use initial condition to find solutions. So, I'll may not solve the full problem, but I'll give you the idea, direction how to solve this problem. So, suppose we consider that problem as a 3-dimensional problem. So, suppose we consider one mass point particle in 3 dimension, subjected to the condition that in cylindrical coordinate, that its rho equal to a and z equal to b phi. So, there are two constants, two independent constants. So, degrees of freedom will be 3 minus 2, because two constraints, two holonomic constraints. So, you will have degrees of freedom equal to 1. Okay. And since we are the constraints are given in cylindrical coordinates, we write the Lagrangian for this particle in 3 dimension using cylindrical coordinates. So, Lagrangian will be again t minus u. So, t in the cylindrical coordinates will be half m rho dot square plus rho square. Cylindrical coordinate is rho phi z. So, phi dot square plus z dot square. So, this is the kinetic energy in cylindrical coordinate, which let me remind you, you can find it using the relation between Cartesian and cylindrical coordinates, y equal to rho cos phi and z equal to z. Okay. So, this if you substitute finding x dot y dot, then t equal to half m x dot square plus y dot square plus z dot square will take you to this kinetic energy. Okay. And now assuming z is the vertical direction, the gravitational potential energy will be mg z. So, now without putting the constraint, the Lagrangian, without putting the constraints, will be half m rho dot square plus rho square phi dot square plus z dot square plus mg z. Okay. Now, constraints rho equal to a, so implies rho dot equal to 0 and z equal to b phi. So, z dot will be b phi dot. So, these are the constants. So, I can use, and so z equal to b phi. So, we can z equal to b phi. So, you can write everything in terms of phi. So, your Lagrangian will be now in phi and phi dot. Notice you had only one generalized coordinate, 1 degrees of freedom. So, Lagrangian will contain only one variable, and that is phi. So, it will be half m. Now, your rho dot is 0, rho is a. So, a square and phi dot square from here, and z dot square will be plus b square phi dot square minus mg b phi. So, this will be the Lagrangian for this system, and it is consistent with degrees of freedom and expected number of generalized coordinate. So, phi is generalized coordinate here. So, you will have, let me simplify a little bit, half m square plus b square phi dot square minus mg b phi. So, this is your Lagrangian. So, very easily you can find the equation of motion that ddt of del L del phi. So, m square plus b square times phi dot will be minus plus mg b equal to 0, minus plus. Okay. So, it will be m square plus b square phi double dot equal to mg b. So, phi double dot will be minus mg b, m get cancelled. So, a square plus b square. And this is a simple differential equation. You can find it will have two second order differential equation will have two constants because second order differential equation, and those can be fixed using the initial condition given in the problem, that rho equal to at rho equal to particle is released from rest. So, phi dot, so at t equal to 0 you have phi equal to 0, this is one condition, and at t equal to 0 phi dot equal to also 0. Okay. So, this is the condition you have to use to find the solution, and you will find the solution. So, this is a nice example to show you use of cylindrical coordinates as well as how to use initial condition to find solution. So, let us consider few more problems. For example, another example. So, example of 2 or problem of problem 2 in this class. So, let me write the problem first. A bead of mass m slides on a smooth rod which is rotating about one end in a, let me write and then I will explain, vertical plane with uniform angular velocity. Say omega. So, you have to construct Lagrangian and its find equation of motion. So, let us how we will solve. So, let me explain this. You have you have a rod, say here, this is your rod, and a mass is sliding down in this along this rod, and this rod is rotating about its one end with the angular velocity omega. So, this rotating with omega. So, what will be the Lagrangian for this system? Okay. So, let us take this is theta. So, this angle, so omega will be so theta will be omega t. Okay. So, this is a very simple problem. So, let us consider the kinetic energy. Kinetic energy will be half m x dot square plus y dot square, but if you consider the r theta, that is x equal to r sin theta, y equal to r cos theta, and then this will be m r dot square plus r square theta dot square, and the potential energy will be minus mg potential energy, which u will be mg h, if this is the h is the height. Okay. So, if this height h, so this will be mg h, and this can be written as mg and r sin theta, because this angle is theta. So, this will be r sin theta. So, it is at r sin theta height. So, the Lagrangian for this system will be L will be t minus u, and can be written as half m r dot square plus r square theta dot square minus mg r sin theta. Okay. So, note that there is a rotation, this mass, the rod is rotating. So, the mass is also rotating, and you can expect some rotational kinetic energy. So, this is the rotational kinetic energy. So, you have the total kinetic energy minus potential energy, and that will give you the equation motion for this system. Okay. So, let us move to some more problems, and because from next class, the lecture 18 will start new topics, symmetries and conservation laws, but today we will concentrate on few more problems or bit complicated problems. So, I will suggest that you solve these problems. So, find Lagrangian this is important. So, one is that suppose you have a spring and it is moving in a in one dimensional one mass one spring, and spring has a constant k, rest length L0, and this has mass m moving in the x. This is very simple problem, and then it is generalized to this problem that you have two mass and two spring. So, this is m1, m2, k1, k2, spring constant, rest length L1 and L2. So, there are infinitely many such problems, mass spring systems you can have, and you can find solution for this. Okay. So now we'll solve two more problems in this class. One is that let me write example 3, which is related to spring. That is why I asked you to solve these simple problems in mass spring systems. So find Lagrangian and equation motion, and you know the equation motion. So equation motion, so find Euler Lagrangian equation motion and match those with the equation of motion for these systems, which is known to you. This you know from your school, that what will be the equation motion for these systems. Now example 3. So suppose you have a simple pendulum. Again we come back to the pendulum problem. So it is a pendulum, but it's not simple. It is the string is replaced by a spring. So the simple pendulum where string is replaced by spring of spring constant K and rest length say L0. Whenever we talk about spring, we always talk about its rest length, and if you don't, then we can assume this length is 0. So this is again a pendulum problem, but and you know how to deal with this problem, but only thing is that when you find there will be additional potential energy due to the spring. So let me fix my coordinate axis, which is x direction, and then this is my y direction. Again degrees of freedom for this will be 1, 2, minus 1. So this will be the degrees of freedom. Okay, so you will have so you will this kinetic energy. So let me write at any time x1, x and y the position of this, then kinetic energy of this will be half m x dot square plus y dot square, and potential energy as will be minus m g y1, because this. Now there is a one point, then what is the constraint equation? So degrees of freedom is actually not 1, but degrees of freedom will be 2, because the length, now your length this x square, it's kind of x square x, it's not L square. No, it will be always L square. So I'm sorry, this degrees of freedom will be 1. Okay. But the spring will have some potential energy which half k, then root over x square plus y square minus L naught whole square. So this will be there as a spring potential energy. So you can again write in terms of, you can eliminate the constraint and you can find the Lagrangian. So Lagrangian you can find. So if I, without putting the constraint, if I write, so it will be x dot square plus y dot square plus mg y, and then minus half k root over x square plus y square minus L0 whole square, and as you know x equal to a L sin theta y equal to L cos theta, and you can substitute and you can find the Lagrangian for the system. Okay, so I ask you to complete this problem, because you can, the simple problem you can find, and also find equation of motion. So again I repeat, I said there was a confusion, but I said the degrees of freedom will be 1. The degrees of freedom is 1, because you have x square plus L square, even though this L changes with the time, but it is a constant, right? So find equation of motion. So last problem today we will consider in next 3-4 minutes is I'll just tell you how to find solution. Suppose you have two pendulum, and both pendulum oscillate in the vertical plane. So you have two pendulum, they are with the fixed point of support, so fixed support. They both are oscillating, it has length L, this has mass m, and this length is say A between the two fixed point, and these two mass is connected by a spring. Okay. So this is, if this is the two pendulum, the two separate pendulum with length L and mass m, both have length L and mass m, they are separated, their point of support is separated by a length A, and then these two masses are connected by a spring of spring constant K, and rest length, you can say that rest length is your A. Okay. So now if you have to find this Lagrangian for this system, so the kinetic energy will be, if you calculate the similar way, it will be half m L square theta 1 dot square and theta 2 dot square, assuming that this angle is theta 1 and this angle is theta 2, and potential energy will be mg 1 minus y1. We are assuming now in this problem we are assuming this is the 0 of potential energy. So potential energy will be 1 minus m1, and for the second mass it will be mg 1 minus y2, and there will be some potential energy due to the spring, half k r minus a whole square, where r we have taken as distance between these two masses, so it will be x2 minus x1 whole square plus y2 minus y1 whole square. This will be your r, and this will be the, so you have potential energy of this, and in this I am in hurry, but you should notice that this is x1 y1, this is x2 y2. So this will be the potential energy. And why it is not minus mg y1? Because now this time I have considered the 0 of the potential energy at the equilibrium position of this. So that is why, but you can naturally see that if 0 of the potential energy is taken at here, then it will be minus mg y1 and minus mg y2. But if we consider 0 of the potential energy at the equilibrium position, that it is 1 minus y1, so it will have only that difference of I am sorry, this will be mg L minus y1, this will be L minus y2. Okay, so please make this correction. So this L minus y1, and so this difference is just mg L for both cases. So these two potential energy is just additional. So your Lagrangian is just differed by 2 mg L by choosing a different point for the 0 of the potential energy. So, it is in your hand where you will choose the 0 of the potential energy. So, now this tutorial class is over. So, in next class we will start with the symmetries and conservation laws. Okay, thank you.